Hi, I'm Tom Metz from Pacific Northwest National Laboratory.
And I'm Crystal Pollitt from Yale University. We're the co-leads of the ChemBio Analytical Sciences Hub of the Network for Exposomics in the United States, or NEXUS, alongside of Randolph Singh from Columbia University and Jeremy Koelmel from Yale University.
Our team is working collaboratively to coordinate community-developed state-of-the-art tools and resources, and to develop best practices to measure the exposome in both biological and environmental samples. As part of the mission of the ChemBio Hub, we are excited to share this educational series with you.
Hi, so my name is Jeremy Koelmel. And as we start to narrow down and understand how to better identify chemicals of the exposome using non-targeted analysis, we're now going to cover isotopes, isotopic pattern, and formula prediction. In the last tutorial, we covered accurate mass and mass defect. But we don't just measure the monoisotopic mass, we measure other isotopes. And this can help us narrow down exactly what the molecular formula is of a chemical species, and also look at subclass, such as chlorinated versus non-chlorinated chemicals. We'll start this tutorial with orthogonal information for chemical identification and where isotopic pattern fits in. Then we'll look into, is accurate mass enough for database matching? Clue, it's not enough, we need isotopic pattern. 3, we'll go, what is isotopic pattern? And 4 is the carbon isotopes and the isotopic envelope, using carbon isotopes as an example to explain this concept. Then we'll go into other diagnostic isotopic patterns for other species such as chlorine, sulfur, and bromine, that are ones that are helpful to keep handy for chemical annotation. Then we'll go into formula prediction. How do we use isotopic pattern to narrow down the possible molecular formula for an unknown candidate? Then we'll go into formula prediction using more complex 11-step workflow that we've developed and integrated into FluoroMatch, and also how we can integrate other orthogonal evidence such as MSMS and homologous series to better annotate our formula. Finally, we'll have a conclusions and our take-home message. So, as we discussed, one of our software platforms we recommend is FluoroMatch, that takes in all the different layers of evidence for both non-targeted and PFAS analysis. And this is one of those layers of evidence, but whether or not you use that software or have general non-targeted approach, all of these pieces of evidence must be incorporated in non-target analysis. So again, MSMS is for structural annotation, accurate mass, and retention time, as we discussed earlier, can give candidates an even narrow down subclass. And isotopes can now narrow down to what types of atoms actually exist in a structure. So why not just use accurate mass to identify formula and possible candidates? So even in 2019, quite a while back, there were 6,792 compounds in the EPA PFAS master list. But the problem was, even with high-resolution instrumentation, most of these overlapped. For example, at less than 0.005 Daltons, which is what most mass spectrometers perform at, 37% of the chemical species in that database had another molecule that overlapped in that mass. And so mass alone wasn't able to distinguish between different chemical species. Of course, this is only looking at the FluoroMatch database. If we included all organic molecules, that overlap would be significantly larger. For example, PFAS at the time didn't have any mass overlap with anything in the EPA database. But if we were to use some large atomic constraints and try to identify all possible formula for that mass, all possible atom combinations that would lead to that mass, for biological elements, we could get 76 possible compounds, not even including a fluorine. And if we added halogenated atoms, we could get 4,446 possible combinations of formula that match that mass within 0.005 Daltons. So we can see that the search space is enormous, and we need a way to narrow down our candidates. That's where isotopic pattern comes in. First, let's explain what an isotope is. So an isotope is the same atom, as you see on the left and the right. This is the same atom because an atom is defined by its nucleus, the number of protons. And so the protons remain the same. In both cases, a carbon has 6 protons, but the carbon-12 has 6 neutrons, whereas the carbon-13 has 7 neutrons. A neutron is about 1 atomic mass units, so the mass of an isotope in this case is +1. We call this M+1. Now, the isotopes also have a natural abundance on planet Earth. So for example, carbon-12, which is much more stable than carbon-13, is the most abundant atom on planet Earth. And so it has about 98.9% relative abundance compared to the 1.1% of carbon-13. So if we look at the carbon isotopic pattern on the left over here, we can see that the carbon-13 in this spectra, the M+1, is about 1.1%. And that's what we'll measure it at. Obviously, we are measuring molecules with multiple carbons, so it's additive. If we have C4F9, which is an in-source fragment of carboxylic acid, you can see that the M+1 is about 4.4%. Now, that's because the molecule has 4 different carbons, and hence each carbon with a 1.1% probability of being C13 has an equal probability. If you add all those up, you get 4.4%. Therefore, the M+1 ratio, and the important aspect of this is you can now tell the number of carbons in your molecule by looking at the M+1 ratio. In reality, while theory says that it should be exactly 4.4%, you can get overlap of other molecules in your mass spectrometry. Your fidelity, or how well your instrument measures isotopic pattern, can be poorer than exact. And so therefore, the 4.4% is an estimate. Often when you get experimental data, it's going to be off of that value. So you won't be able to get the exact carbon number, but you can narrow that down often. Now, it's interesting that while we have only 2 isotopes of carbon, we can get multiple peaks. So for example, while the M+2 is extremely low, because the probability of getting 2 carbons is 0.01 times 0.01, there are many combinations of 2 carbon species, and so there is a small probability in this C4F9 of getting 2 carbons. Now, if you look at a molecule that's much larger, the isotopic envelope gets much more complex. So what we call the isotopic envelope is all of the isotopes that belong to that molecule. And often, especially with carbon, they follow a pattern such as this, where if you have, for example, in a buckyball, 60 carbons, then you will see this decaying pattern of M+1, M+2, and M+3, M+4 as the probability gets lower and lower for those additional isotopes. Note, for peptides and proteins and larger molecules, your isotopic pattern might actually look very different, where the M is not the dominant species, because the probability of getting 1C13 starts to grow. For example, if I had 100 carbons, we'd have 110% probability of an M+1, and so it'd be larger than our M. Not 110% probability, sorry, 110% relative to the M ion. Now, beyond carbon, there's a lot of other atoms that have isotopic patterns. Well, I should say there's a few. So here are some of the common elements on the periodic table, and you can see their isotopic pattern. So carbon has a tiny isotopic pattern, but it's useful because we see enough carbons where that signal is strong enough. Remember, in an environmental sample, our xenobiotics or contaminants of concern might be at very low abundance. And so if there was only one carbon, we wouldn't actually see the isotopic pattern and couldn't do anything about it to help discern the formula. So luckily we have lots of carbons, and that's why the carbon isotopic pattern is useful. On the other hand, while nitrogen and oxygen might have tiny peaks for their isotopic patterns, they're not monoisotopic, meaning they have multiple isotopes. They're so low that they're often not visible or useful, again, depending on the signal of that molecule. Certain atoms, such as fluorine, don't even have isotopic patterns, and therefore that leaves us with only a few molecules that are very useful in their isotopic pattern. Boron in this case could be useful, but it's less common to be found in our exposomic studies. So that leaves carbon, silicon, sulfur, chlorine, and bromine as the main atoms with isotopic patterns that are useful to understand and look for in your mass spectrometry data. So if you memorize these isotopic patterns and know how they behave, you'll be off to a very good start. Here's a zoom in on some of these patterns. So here's the sulfur isotopic pattern. It has an M+2 at about 4%. Here's the chlorine isotopic pattern. It has an M+2 at about 30%. And so these are pretty strong M+2 isotopic patterns that don't often overlay with your carbon isotopic pattern where the M+2 is low, at least for small molecules. And therefore, these can be diagnostic. If you have a sulfur-containing species, you may be able to tell that from the M+2. If you had 2 or 3 sulfurs, of course, you would be able to tell how many sulfurs are there based on the isotopic pattern. Same thing with chlorine. Even one chlorine, and even for a low abundant molecule, you can still very often see the isotopic pattern because it is very high at the M+2 and very clear. If you had multiple chlorines, they form a very unique distribution, and so it's very easy to predict how many chlorines are in a species and determine chlorinated species. So let's say you're doing an exposomic study and you want to see exposure from one of the most important parts or exposures that we face today, according to Susan Richardson at least, which is chlorinated drinking water. You'd be able to find some of these chlorinated products very easily using their isotopic pattern, so this would be a very powerful tool. Let's look at PFAS versus PFOA to see how this works when we have an intact molecular species. So here's PFAS, which is a 8-carbon species, and it's also sulfonic acid, so it has a sulfur, and it has 3 oxygens, which again are barely going to contribute to the isotopic pattern. Here you can see a decent sized M+2 peak and an M+1 that gives evidence of 8 carbons. PFOA, on the other hand, you still have the M+1 giving evidence of the 8 carbons, but you have a very small M+2 peak because you don't have sulfur in the species. Therefore, for example, if you're looking at detergents with sulfur versus non-sulfur or PFAS with sulfur versus non-sulfur, this isotopic pattern can be very powerful to distinguish these. Now, beyond looking for 1 or 2 atoms and determining whether those atoms exist, you can also use isotopic pattern for formula prediction. For formula prediction, you have an accurate mass and you have arrangements of atoms that could lead to that accurate mass. Similarly, if you have an isotopic pattern, then you can have arrangements of atoms and see if they lead to the same isotopic pattern. For example, on the top diagram here you have in gray is often shown your experimental isotopic pattern, and in the non-filled diagram below it, these could be your theoretical isotopic pattern. And the better a mirror image you have, the more likely this is to be your candidate. So this is data, for example, from, again, PFAS. Now you can see even if you rank the dot product, which is how similar the experimental versus library spectra is, cosine usually is what's used to normalize it to 1. your PFAS might not be the top ranked candidate, even if it's the correct candidate. And that's because many different combinations of atoms can lead to the same isotopic pattern. If we look at the top candidate, it has 8 carbons, so again, it should have the same N+1 as PFAS. It also has 1 sulfur, so again, it should have the same N+2 as PFAS. It has 18 oxygens, though, that will start to contribute to the isotopic pattern. So might be filling in for the error in your instrument, where you have slightly different isotopic patterns. Sometimes the formula prediction will fill that error with oxygens or other species that add a small amount to that isotopic pattern. So even though this is the top candidate, it's not correct. So we need orthogonal information. Isotopic pattern is not enough. Another piece of information you can use, for example, is fragmentation. If you have MSMS fragments, especially low mass fragments, such as C2F5, then you know at least there's 5 fluorines in it and 2 carbons. And so we could eliminate that first candidate because it doesn't have 5 fluorines. So your fragmentation can be used to narrow down your formula predictions as well, but we don't always have fragmentation. The other thing we can do to narrow down formula predictions is to see whether those structures are possible. So can you form a Lewis dot structure for them? Or probable. So in this case, all 4 of these species technically are possible, although they would be highly unstable, but they're highly improbable. A species with 18 oxygens is very unlikely to occur when it only has 8 carbons, plus another 8 hydrogens that have to attach to those carbons, sulfur that has to attach to those carbons, and fluorine. So, in that way, this is a highly unlikely formula. So in that way, we can eliminate unlikely formulas, and when we do that, we're left with PFAS. So here's a more sophisticated step-by-step look at how we do formula prediction in FluoroMatch, which gives an idea of the different steps that we can use to narrow down these candidates, even if we have a nice isotopic pattern. So this algorithm was developed by David Schiesel, who works with Innovative Omics and Babcock Labs. So what David Schiesel developed, this workflow, is first, when you have mass spectrometry data, we haven't gotten to the nitty-gritty of this, but you're going to run many samples. So let's say you have 100 contaminated soil samples or 100 blood samples. They're going to have different levels of different PFAS in each sample. And so you want to take the sample with the highest level of the candidate of interest so that you have the highest signal. So that's what we do. We extract the MS spectrum with the highest signal across all samples. Then we know an isotope is just the mass of additional neutron plus any changes in the binding energy, which often are very small. So we use a neutron mass filter, which is slightly outside of your mass accuracy to account for the binding energy, and then we can identify the isotopic envelope, those peaks that are only from your isotopes, and remove any other peaks, which gives us a clean isotopic spectra. For example, in green here, with all red removed. That's your isotopic envelope we discussed earlier. Then, it's always important to look at the quality of the information you have. If you have garbage information, you don't want to do complex algorithms, give the user or your person you're giving a report a potential candidate when that candidate is based on faulty or poor information. So, for isotopic pattern, let's say that the ion is too low to see any isotopic peaks, so you only get 1 peak. It's going to be very difficult to predict formula, so you may want to skip that. Or you might get an isotopic pattern with a lot of noise and a lot of other peaks that overlap. You also might want to skip that. So there's quality filters so that we're only looking at those isotopic envelopes that are clean enough to get good candidate predictions. Now, like we talked about before, certain elements like carbon, chlorine, bromine, and sulfur, have very unique isotope patterns. So if we don't see an N+2 at a high level for a very small molecule, we know there's no sulfur. If we don't see an N+2 around 30%, we know there's no chlorine. And so in that way, we can limit the atom or atomic constraints, so the types and number of atoms that go into our formula prediction based on the isotopic pattern. Then you generate all the possible formula that can match that accurate mass. And that's often hundreds of molecular formula, especially for higher mass species. But then after that, you can reduce these formula candidates by, for example, applying the nitrogen rule, determining whether the structure is even possible, what are some common element ratios. So for example, you wouldn't expect 50 hydrogens to 1 carbon. Usually it'd be 2 or 3 to 1 carbon. And so what are some common element ratios, and then reduce those formula to those ratios. Finally, you can have some candidate formula and match your theoretical isotopic pattern to your experimental, like we discussed earlier, and rank your candidates. And of course, after that, that doesn't have to be the end of your formula prediction, although you may have some candidates that are correct there, and even sometimes your top ranked one is the correct one. You now want to use all the other evidence that we discuss in these trainings to narrow down that formula. For example, homologous series, which we discussed in the last tutorial, are a really good way of classifying features or chemicals that belong to the same subclass. So for example, let's pretend this is a Kaufman plot where you have your nice line of features, and on the y-axis is your normalized mass defect, on the x-axis is your mass to charge. They'll form a nice straight line, and you can be sure, especially if the retention time trend is very clear, that these belong to the same subclass. If they belong to the same subclass, they should have the exact same formula, except for the carbon-fluorine chain, in this case, should differ. So, if you have a large number of candidates, let's say, and for these 5 features, 3 of them are sulfonic acids, just differing in carbon-fluorine, based on your formula prediction, then you can know for the rest of the series that these are the correct candidates. And even if these other 2 features in a more tealish blue are not sulfonic acids as their top formula prediction, we can use a vote and say whichever formula predictions across all the features of that homologous series gave the same subclass, these are probably the right subclass and the right formula prediction. And what we find is this works extremely well. So this was developed by Michael Coomer, David Schiesel. Actually, the idea was from Emma Rainey from Agilent. And so, for example, NIST-A, which is a spiked 12 standard spiked into solution that we were able to detect, we were able to get a 17% false positive rate for formula prediction, just using the 11-step formula prediction we showed earlier. So 17% is pretty good, but that's still about 1 out of 5 is wrong. But when we use homologous series voting, so we use information from all the other members of the homologous series in terms of their formula predictions, we get a 0% false positive rate. So highly accurate. And that's going to narrow down our database searches if we actually know the specific formula for our species. And even if there is no database available, having a molecular formula is a great start for de novo structural elucidation. Now let's look at NIST-C, which is an AFFF or aqueous firefighting foam contaminated soil. Now we were able to identify 151 species using different methods we'll discuss later, but with very high confidence. And of these 151 species, we got a 26% false positive rate in terms of formula prediction. 1/4 of the time about, the formula prediction that was given was not the correct formula. But again, if we use homologous series voting, so we take the formula prediction from each homolog and use that information together to predict one formula for the entire series, we got a 0% false positive rate. So when there is homologous series, of course, our false negative rate goes up because certain features don't have homologous series. But when there's homologous series, we can get a very high confident formula prediction. So this is very powerful. And as we noted, there's other pieces of evidence we can add as well, even without homologous series, like fragmentation, that can reduce the false net positive rate. So in summary, isotopic patterns are the same atom with different neutrons. That's all they are, but they give very important information for us mass spectrometrists to identify chemical species and their molecular formula. Certain atoms have diagnostic patterns, for example, carbon, sulfur, chlorine, and bromine, and these are going to be the main useful ones for determining atomic composition of a feature. And then when we use isotopic patterns, along with orthogonal information, we can get unequivocal formula prediction. So formula prediction we can be highly confident in, which is both helpful on its own for trying to determine what types of species we have. We might know they're fluorinated if the formula prediction can only be done for a fluorinated species. We might know they're chlorinated, especially because chlorines have such a strong isotopic pattern. We know that they're chlorinated and probably chlorinated drinking water product if we're looking in water treated with chlorine, for example. And so we can use that as a screen. But also they serve the formulas as a starting point for de novo structural elucidation, which is extremely important as well.
Thank you for watching. If you have any questions or suggestions for future topics, we welcome your ideas. To stay informed about the latest developments in exposomics, please visit our website and subscribe to our monthly newsletter from updates from across the field. Be sure to explore the NEXUS podcast on YouTube and Spotify, and follow us on LinkedIn, X, and Blue Sky and NEXUS Exposomics to stay connected with our community. Thank you for being a part of our NEXUS network.